This is lesson 6 of module 4, where we're talking about vectors. In this lesson, we're talking about rotating the axes. So when we have a vector is defined by its magnitude, that's the length, and the direction of the vector, which is the orientation of that arrow, the direction that that vector quantity is pointing in. Thus far, we've used an angle phi to describe the direction of that vector, but that's relating the direction of our vector to the direction of our axes here, which we default to using horizontal and vertical axes as our standard axes. But that doesn't have to be the case. Our axes here are a mathematical construct that we use in order to facilitate our measurements of the vector and of other quantities. But that is something that we have introduced as a crutch and doesn't have anything to do with the vector itself, which is a measurement of a real quantity that exists outside of our model, outside of our attempts to measure it. So we may want to measure this vector not against the standard axes, but for example, we might want to use inclined axes if we have an object that is moving up a ramp or up a hill, up some sort of incline. And that would be perfectly fine for us to do. The thing is, we must not change the vector itself. The vector is a measurement, and we have to define the direction of our vector. We have to maintain the magnitude of the vector and maintain its orientation, maintain the direction that the vector is pointing. However, we can give it a new direction, phi prime, that is measured relative to our primed axes. Instead of x and y, we could use x prime and y prime as a new set of rotated axes that are rotated in angle theta from the original ones. And if we measure this vector relative to the new axes, we'll have different components than we originally did, but we have to have the same magnitude of the vector, and we have to be pointing along parallel lines. If we do that, then we have the same vector in both cases, and we simply have different components measured relative to different axes. So the key to dealing with rotated axes is to put the vector in polar form, find the magnitude and the angle. The magnitude stays the same, and when you rotate the axes, the angle is going to change plus or minus the angle of rotation. In this case, phi is measured from true horizontal to the direction of our vector. So this angle here is still phi. And so we can say that phi prime would be phi minus theta in this particular case, which means we have a larger x prime component. We're closer to being aligned with the x prime axis. We have a smaller y prime component. Note that the components are always parallel to their axes. The x prime component is parallel to the x prime axis. The y prime component is parallel to the y prime axis. The x component is parallel to the x axis. The y component is parallel to the y axis. But you're simply adding or subtracting that angle of rotation to the direction of the vector, keeping the magnitude of the vector the same. Once you have the new angle, you can use sines and cosines to find the x and y components.